Okay, so let's move on to chapter 10.5, which is relationships between hypothesis testing procedures and confidence interval. So what would be the relationships between hypothesis testing and confidence interval? And actually they are very closely related. If zeta hat is an estimator for zeta and zeta hat has an approximately normal distribution, the two-sided confidence interval for zeta is calculated this way. And let's think about we are interested in alpha level test of this hypothesis test. Zeta is equals zeta 0 as H null hypothesis versus two-sided alternative, which is zeta is not equal to zeta 0. And we would like to use following Z as our test statistic, this one. And from this test statistic, we can derive the rejection region. The rejection region. So the complement of rejection region. The complement of rejection region. We can write it as this or rejection region complement. So complement of rejection region is actually acceptance region, and in that two-sided test, the acceptance region can be written as this, and actually we can rewrite this expression this way. So here z is zeta hat minus zeta 0 divided by sigma zeta hat. And so we can rewrite this acceptance region this way, and again we can write it with respect to zeta 0, then we can rewrite it this way. And as you can see, this is exactly the 100 times 1 minus alpha percent two-sided confidence interval for zeta. So, so hypothesis testing procedure and confidence interval are highly related because the underlying distribution, actually this start from the same distribution. So so hypothesis testing and confidence intervals are closely related. Previously, we learned about the two-sided case, and let's think about one-sided case. Actually, this is from exercise problem 10.46. A large sample alpha test of hypothesis for H0 is zeta 0, and H alternative is zeta is greater than zeta 0. Reject the null hypothesis if this is true. Okay, and show that this is equivalent to rejecting H0 if zeta 0 is less than the large sample 100 1 minus alpha percent lower confidence bound for zeta. So the confidential bound for this case is zeta is greater than zeta hat minus z alpha sigma alpha hat. So this is 100 minus 1 minus alpha percent of lower confidence interval bound. And from here, from this test statistic, the rejection region is this one. Zeta hat minus zeta 0 divided by sigma zeta hat is greater than z alpha, and this is actually zeta hat minus z alpha sigma zeta hat is greater than zeta 0. So this is the rejection region, and the acceptance region is the complement of rejection region, which is zeta 0 is greater than zeta hat minus z alpha and times sigma zeta hat. And so we can check that the confidence interval and acceptance region is exactly same. This is and and so we can check the consistent result from the previous one for the one-sided case as well. And the problem 10.48 is also another direction, which is alternative hypothesis is zeta is less than zeta 0, and I will leave it to you, and let's move on. Let's move on to exercise problem 10.47. Refer to exercise 10.32. Construct a 95% lower confidence bound for the proportion of the nation's adults who think the quality of the environment is fair or poor. Okay, so before we construct a 95% lower confidence bound for this, we should read exercise problem 10.32. In March 2001, a Gallup poll asked how would you rate the overall quality of the environment in this country today, as excellent, good, fair, or poor. Well, we have 1060 adults, this is our N, and 46% gave a rating of excellent or good. Is this convincing evidence that a majority of the nation's adults think the quality of environment is fair or poor? Okay, so the quality of environment is fair or poor. The percentage of this thing, let's define it as P. So test using alpha equals 0.05. So our null hypothesis is P equals 0.5, and our alternative hypothesis is that the P. The majority of the nation's adults think that the quality of environment is fair or poor. The majority, which is greater than 0.5. So this is our alternative hypothesis. And what is our test statistic? Our estimator for p hat, which is 0.54. So 46% gave a rating of excellent or good. So 54% gave a rating of fair or poor. So our estimate is this p hat, and I will skip the proof of the 10.32. Do it yourself, and I will move on to 10.47 again. So construct a 95% lower confidence bound for the proportion of the nation's adults who think the quality of the environment is fair or poor. So equation for this one, the confidence interval is that this is the P is greater than 0 P hat minus Z alpha times sigma P hat, and this one P hat is 0.54, Z alpha, when alpha is 0.05, this one is 1.645, and this sigma p, it is square root of p hat times 1 minus p hat divided by n. And so if you plug in n equals 1060, this is 1060, p is 0.54 and 0.46. So if you plug in and calculate this number, you will get the 0.5148. So this is our confidence interval. And how does the value p is 0.50 compare to this lower bound? And actually this one is not inside of the confidence interval. So what this means is that we we will reject the null hypothesis and we will accept the alternative hypothesis. And so based on the lower bound in part A, should the alternative hypothesis of exercise 10.32 is accepted? Yes, actually we should accept the alternative hypothesis and we reject H0, reject H0, reject H0. Because the 0.5 is not inside of the confidence interval, so we reject at H0. That means we are accepting the alternative hypothesis. Okay, and number C, is there any conflict between the answer in part B and your answer to exercise 10.32? And if you do the hypothesis testing for 10.32, you would reject the null, so there should be no conflict, and so there is no conflict. Okay. Homework for 10.5 is this. Let's move on to chapter 10.6. Another way to report the results of a statistical test. Attained significance level or p-value. We call the p-value attained significance level or p-value. We call it this way. Most of times we call p-value. And let's see what it is. If W is a test statistic, the p-value or attained significance level is the smallest level of significance alpha for which the observed data indicate that the null hypothesis should be rejected. And actually, this one, what it means is this thing. So, so in this situation, the alpha is the probability of reject H0 when the H0 is true. When H0 is true. So alpha is the probability of rejecting H0 given H0 is true. And actually, if we get the statistic, if we get the test statistic W, then we can calculate this probability directly from our test statistic. The probability of our test statistic is rejected. Test rejected. Test rejected. Given the H0 is true. So this is p-value. P-value. That is this thing. So the alpha, the probability of rejecting H0 given H0 is true, we have the underlying distribution. We have distribution for the null situation, which is this. And if you fix the number alpha, then you can get the decision rule. So if we have something that is inside of this region, then we will reject the null hypothesis. That's our decision rule for the test. And if we get the test statistic, and actually we can calculate the area here. Actually, we can calculate the area here. And this is the p-value. So it is the we can say that this is the smallest level of significance alpha for which the observed data indicate the null hypothesis should be rejected. So if alpha is at this level, then we can still reject the null hypothesis. So this amount would be the smallest level of significance. Maybe this expression maybe not good expression. So just to remember the definition and the meaning of this p-value is this one. Okay. Let's move on to example 10.10. Recall our discussion of the political poll where n equals 15 voters were sampled. If we wish to test H0 is P is 0.5 versus alternative is P is less than 0.5, using Y is the number of voters favoring Jones as our test statistic. So Y is our test statistic, and what is the p-value if Y is 3? So here the Y, the number of voters favoring Jones, follows binomial distribution with NP. N is 15 and P is, under the null hypothesis, the P is 0.5. And so the distribution of Y, so 7 or 8 from 0 to, the distribution would be something like this, 7, 8, something like this, and the rejection region would be somewhere here. Y is less than k. This would be rejection region. For alpha, you can calculate if alpha is decided, and actually that's not needed. We want to calculate the p-value if y equals 3. So what we want to calculate is probability of y is less than or equal to 3, because if y is less than or equal to 3, we can reject the null hypothesis. This is okay, and since y follows binomial distribution of this one, probability of this thing, we can calculate it using R, and this is 0.017, something like this. So this is our p-value. So our p-value is this one. Okay. Let's move on to example 10.11. Find the p-value for the statistical test of example 10.7. So example 10.7 is like this. A psychological study was conducted to compare the reaction times of men and women to a stimulus. Independent random samples of 50 men and 50 women were employed in this experiment, and the results are shown in table 10.2. Do the data present sufficient evidence to suggest a difference between the true mean reaction time for men and women? Use alpha equals 0.05. From here, the test statistic is y1 bar minus y2 bar. Actually, what we know is that y1 bar minus y2 bar follows normal distribution with mean 0. Under the null hypothesis, it follows mean 0, and the standard deviation, which is sigma square over n1 plus sigma 2 square n2 of this, and since we don't know exact the variance of the first group and second group, we can replace it with the sample standard deviation, sample variance, which is s1 square and s2 square. And so our test statistic z is defined as y1 bar minus y2 bar divided by square root of s1 square over n1 plus s2 square over n2. Okay, and we can calculate this z value. So y1 bar is 3.6, y2 bar is 3.8, and the s1 square is 0.18 over 50 plus 0.14 divided by 50. And if you calculate this quantity, this one is minus 2.5. And so if we want to reject this test, so this z follows normal distribution, and to reject this test, we need to the p-value would be outside of this. The p-value would be this region, which is this one. So we can calculate the probability of z is larger than absolute value of z is larger than 2.5, and actually this is 2 times probability of z is less than minus 2.5, and we can calculate this probability of z is less than 2.5 by using r p norm minus 2.5, using r command p norm minus 2.5. This will give you about I don't know, but this one times 2, it will give you about 0.0124, 0.0124, and so this is your p-value. This should be your p-value. Okay. Let's move on to exercise problem 10.52. A biologist has hypothesized that high concentrations of actinomycin D inhibit RNA synthesis in cells and thereby inhibit the production of proteins. An experiment conducted to test this theory compared the RNA synthesis in cells treated with 2 concentrations of actinomycin D. Level is 0.6 and 0.7 microgram per liter. Cells treated with the lower concentration of actinomycin D yield that 50 out of 70 developed normally, whereas only 23 out of 70 appeared to develop normally for the high concentration. Okay, so we have 2 type of concentration, 0.6 and 0.7. For 0.6, the 55 over 70 developed normally. However, from 0.7, 23 over 70 developed normally. Okay, do these data indicate that the rate of normal RNA synthesis is lower for cells exposed to the higher concentrations of actinomycin D? Okay, so what is the hypothesis? H0 is P1 is same as P2, and H1 is P2 is less than, so P1 P2 is less than P1, which is same as P1 minus P2 is greater than 0. Okay, and what would be the test statistic for this case? That is P1 hat minus P2 hat. This is P1 hat, and this is P2 hat, and this one would follow normal with mean 0 and the standard deviation, which is P1 1 minus P1 divided by N1 plus P2 1 minus P2 divided by N2, and here N1 and N2 are both 70, and here what would be the null hypothesis? The null hypothesis is P1 equals P2, and there's no difference in the null hypothesis. So in null situation, the estimate of P hat would be 55 plus 23 over 140. So from here we can calculate the null p hat, and we will put p hat here, p hat here, because we are calculating this distribution under the null situation, under H0. So we are calculating this one under the null situation. So this is it. And so let's calculate our Z statistic, which is P1 hat minus P2 hat. So 55 over 70 minus 23 over 70 divide by square root of 78 over 140 times 1 minus 78 over 140 divide by 70, and we have two of these. Okay, and if you use your calculator to get this number, this one is 5.443, and so the p-value is probability of z is greater than 5.443. And if you use the r like using 1 minus p norm 5.443, then you will find this is very close to 0, and so you can say that your p-value is very close to 0. And so so p-value is close to 0, close to 0. And if you choose to use alpha equals 0.05, what is your conclusion? Your p-value is less than alpha, so you will reject the null hypothesis. Reject null hypothesis. Okay. The homework for 10.6 are these.